كان جو Mesbah.
Hello. So thank you for the invitation. Thanks for the host for making this happening. So the topic that I will talk about today is three-dimensional hyperbolic manifolds. We will focus on that. In this talk, we will focus more on the interaction between hyperbolic manifolds, convex hyperbolic manifolds, and more precisely convex cocompact hyperbolic manifolds that I will define later, and their boundary. And so first, let's start by introducing the hyperbolic space. So the hyperbolic space has many models, has many equivalent models, but for us, we will use this one. So we take the Euclidean ball, the usual Euclidean ball, and instead of putting on it the usual Euclidean metric, we put this metric here, the square. So as you can see here, we are multiplying the Euclidean metric by conformal factor, and this conformal factor goes to infinity when we are closer to the boundary. So the ball with this metric is a complete space, and it has infinite geodesics because the fact that the conformal factor goes to infinity when you are closer to the boundary. So if you take a geodesic from the boundary to some point inside the ball, it has an infinite length. And since the conformal factor is equal to infinity when we are in the boundary, so the metric doesn't extend to the boundary of the ball, which is S2. But because it is conformal to the Euclidean metric, it induces a conformal structure on the boundary. And this conformal structure is so the boundary of the ball with the conformal structure is the usual conformal structure of S2, which is also CP1. Another fact is that the isometry group of the hyperbolic space that preserve orientation, so the elements that preserve the distance, the elements that the maps from by isometry, I mean the map from H3 to H3 that preserve this distance, ds square. This metric, sorry, ds square. The elements of isometries that preserve orientation form a group which is isomorphic to PSL2C. So we can see the isometry group of H3 that preserve orientation as PSL2C. And then we define a hyperbolic tree manifold. A complete hyperbolic manifold is defined to be the quotient of H3 by gamma for some gamma which is a discrete torsion-free subgroup of PSL2C. So any complete hyperbolic three-dimensional manifold is the quotient of H3 by a discrete torsion-free subgroup of PSL2C, which is the isometry group of H3. So here we will give an example of such three-dimensional manifold. So one example, one of the simplest example that about this how we construct three-dimensional hyperbolic manifold. So first, we start by taking sigma to be closed, connected, oriented surface of a genus bigger or equal to 2. So just as a reminder, we have a classification. We have a full classification of closed, connected, oriented surfaces. They are the torus and these surfaces that have genus bigger or equal to 2 and the sphere. We know that the sphere has can be undo only with spherical metric. That is a metric that has curvature equal to 1. We know that a torus can undo it with metric that has constant curvature equal to 0, flat metric, and the other metric that can be on the other surfaces that can be endowed with the hyperbolic metric, that is a metric that has constant curvature equal to -1, are the surfaces that have genius bigger or equal to 2. Yes, so we already have full classification for that. So for us, we will take a hyperbolic surface. A hyperbolic surface, it is this type of surface, a surface with genius, closed surface with genius bigger or equal to 2. And then we go back to the hyperbolic space. So as I said, the hyperbolic space is the ball on the wood with that metric that we have defined. So here we take the plane x3 equals 0, the one here that you see in the blue and has boundary in the red. H3 has a metric that we have defined, and this metric, it induces also a metric on this submanifold, which is the plane x3 equals 0. And it happens that the induced metric on this plane is isometric to the hyperbolic plane. So the hyperbolic plane, we can define it exactly as we can define it in the same way as we defined the hyperbolic space. We just take 2 coordinates instead of 3. And when we take a plane like this, for example, x3 equals 0 inside the hyperbolic space, the metric of the hyperbolic space induces a metric on this plane that makes it isometric to the hyperbolic plane. And the subgroup of the isometries of H3, which is PSL2C, that makes this plane invariant under its actions, form a group which is isomorphic to PSL2R. And also here I should recall that PSL2R is the subgroup, the group of isometries of H2 that preserve orientation. So this group is isomorphic to PSL2R. And now we define a representation, Fuchsian representation. So here by representation, I mean a homomorphism from the P1 of the surface sigma and to some group. Here we take PSL2C. For us, a representation is a homomorphism from the P1 of sigma to PSL2C. And we say a homomorphism that a representation is Fuchsian if it factors in this way. So it factors into some representation into PSL2R, that is its elements makes this plane invariant. This plane, which is a geodesic copy of H2, so the H3 invariant. And then we see it in PSL2C. And now we can define the first three-dimensional manifold in this talk, what we call Fuchsian three manifolds. So here we take a Fuchsian representation, and then we take the quotient. So when we take the quotient, we get something like this shape in the right, like something which is topologically sigma times R. And this totally geodesic copy of H2, its quotient will be a hyperbolic surface, which is isomorphic to H2 over rho 0, and the three-dimensional manifold, which is H3 over rho, is topologically sigma times R and has this metric here, ds square, where H is the metric of the totally geodesic surface in the red. And we know in function of this metric, we know the metric of the three-dimensional manifold. Now we can define, we will define quasi-Fuchsian manifolds which will be our main objects that we will talk about during all of this talk. So first, to define this, let's define what is the limit set of of a representation, of a discrete fight for the representation. So we take we take a representation which is discrete and fightful. Yes, so when a representation is discrete, it acts properly discontinuously, so we don't have accumulations inside the space. And we take any point P in the hyperbolic space, and we see its orbits under the action of this representation rho. So since this representation is discrete, then it will act properly discontinuously on H3. So we won't have accumulation points inside the H3, inside the body. This won't happen. So what will happen? The orbits of P will accumulate in the boundary at infinity, which is S2. And we define the limit set to be this accumulation point that they are in the ideal boundary. So and also it happens that this notion, it doesn't depend on the initial point that we take. So if I take another P, another point here, we will have the same limit set. And we define the domain of discontinuity to be the ideal boundary of H3, which I recall that it is S2, minus the limit set. And we know, in fact, for people who do hyperbolic geometry, is that in this case, the representation acts properly discontinuously on H3 union the domain of discontinuity. So in other words, the representation acts properly discontinuously on H3 with the ideal boundary minus the limit set. So we just need to remove the limit set to be able to talk about quotient. And we define a quasi-Fuchsian representations to be a representation in which its limit set is Jordan curve. So as the image here, because the limit set it's not always Jordan curve. It can be any it can be complicated things. Yeah, but in this talk we will focus on this when the limit set is a Jordan curve. And we define a quasi-Fuchsian manifold to be something isometric to the quotient of H3 by a quasi-Fuchsian representation. So in other words, quasi-Fuchsian manifold is the quotient of H3 by quasi-Fuchsian representation. And then we define the set of quasi-Fuchsian manifolds to be the set of quasi-Fuchsian representations modulo action by conjugation of PSL to C. And yes, something that we should know is that this point of view of the set of quasi-Fuchsian manifolds, I mean, when we see it as representations, it allows us to define a topology on the space of quasi-Fuchsian manifold, and even more. We can go until a complex structure. So the set of quasi-Fuchsian manifolds has natural complex structure, which comes from this point of view when we take it as a representation. Later we have this theorem by Marden that's saying that it's studied how quasi-Fuchsian manifold looks like. So the theorem states that if the quotient of H3 by quasi-Fuchsian manifold is diffeomorphic to sigma times 0, 1. So the same case as Fuchsian three-dimensional Fuchsian manifold that we have seen. And when we add the ideal, but the domain of discontinuity, then it will be diffeomorphic to sigma times 0, 1 closed. But here one should notice that in that case, when we add the domain of discontinuity, we don't have a metric on the boundary, which is sigma times 0 union sigma times 1. We don't have a metric because the hyperbolic metric doesn't extend to the ideal boundary, as we have seen, because of that conformal factor that goes to infinity. So here we don't have a metric, but we have another data that we will talk about. So it's true that we don't have a metric, but we have as we have seen, we have a natural conformal structure on the ideal boundary of H3, which is the same conformal structure of the sphere. And when we take some Fuchsian group, some quasi-Fuchsian group, which is a group which has a limit set, which is a Kleinian group that has a limit set Jordan curve, and it acts properly discontinuously on H3 union the domain of discontinuity. When we take the quotient, we also quotient the component of domain of discontinuity, which is two topological disks, because it has two minus Jordan curve. It gives us two topological disks. So we call them, for example, omega plus and omega minus. Then omega plus, the quotient of omega plus by the Fuchsian group gamma give us a conformal structure, and also we gave us a conformal structure on the surface sigma, and also the quotient of omega minus by gamma, by the action of gamma, give us also a conformal structure on the surface sigma. So when we take a quasi-Fuchsian manifold, we naturally have two conformal structure on sigma, coming from the quotient of the domain of discontinuity by this quasi-Fuchsian representation that we took. And here we have this theorem of Bers that give a full identification between quasi-Fuchsian manifolds and their ideal boundary. So the theorem states that this map here that we have seen here, you take quasi-Fuchsian manifold and you associate to it the conformal structure on the ideal boundary. Yes, so the ideal boundary is the quotient of the domain of discontinuity by your group, by your representation. This map that associate to quasi-Fuchsian manifold, these two conformal structures, gamma plus over gamma and omega minus quotient by gamma, it is a biholomorphism. So it means that when we talk about quasi-Fuchsian manifolds, we can understand all the study of quasi-Fuchsian manifolds, the study of their ideal boundary in some sense, because we have a full identification. Yeah, also it's worth to see that the space of quasi-Fuchsian manifold is biholomorphic to Teichmüller times Teichmüller of the surface. Yes, so the Teichmüller space for the surface may be many of you already know what is Teichmüller space. Is the isotopy, the conformal structure on the surface modulo isotopy, or equivalently the hyperbolic matrix on the surface modulo isotopy. So the key point that the key point here is that quasi-Fuchsian manifolds in some sense can be identified where the ideal boundary, because of this biholomorphism that Bers has shown. And then we can talk about other data on the boundary. So here we have seen that the conformal boundary give us like all the information about the quasi-Fuchsian manifold. But can we say more? Can we see other data? Or this is what we will see. So here we define the convex hull. So the convex hull is just you join your set by all these possible geodesic segments, and you get to the convex hull. It's exactly as the Euclidean convex hull. So here we take a representation, quasi-functional representation for us, and we take its limit set, and we take the convex hull of the limit set. Yeah, so quasi-functional representation has a Jordan curve as limit set. And this allows us to know that the convex hull of the limit set of quasi-function representation is homeomorphic to the sphere, and its boundary inside H3. So we take the boundary minus the Jordan curve. We don't take the ideal boundary. Is two topological disks. We do not like that. And also an important thing is that they are not smoothly embedded. They have another structure that we will talk about later in this talk. But the hyperbolic metric of H3 induce a path metric on this boundary, on that boundary. And it happens that the boundary of the convex hull with this hyperbolic metric, with this path metric, is isometric to the hyperbolic plane H2. And now when we go to the quotient, when we take the quotient of H3 by the quasi-functional representation, we call the quotient of the convex hull by the convex core, and we will get two hyperbolic metrics on sigma doing this process. So we take quasi-functional representation, we take the convex hull, we quotient, and when we quotient, this convex hull will be some manifold that has two disjoint, the boundary that consists of two disjoint copy of sigma, which is not smoothly embedded. We will talk about this structure later, and it will induce two hyperbolic matrix on sigma. Yeah, so here is another picture. So you have we take quasi-function manifold, we quotient the convex hull, and the convex hull will be something which is homeomorphic to sigma times 0, 1, and the induced metric on sigma on the quasi-function manifold would induce two hyperbolic metrics on sigma h plus and h minus. Yeah, this is because in the cover in H3 it induces the path metric is isometric on the boundary of the convex hull is isometric to H2. That's why when we quotient it is it gives us two hyperbolic metric on sigma. And there is a conjecture by Thurston saying that and this correspondence that when you take quasi-function manifold and you associate to it the metric on your surface sigma, the two metrics on the surface sigma coming from the boundary of the convex core. A conjecture that this map is a homeomorphism. So which is something similar to in some sense similar to Bers theorem. So Bers theorem have shown that the conformal structure on the ideal boundary and the quasi-function manifolds, this map is a biholomorphism, and Thurston said that the map that associates to quasi-function manifold, the hyperbolic matrix on the convex core, is a homeomorphism. Yeah, so for this question is still open, but we know surjectivity. The surjectivity is known, but the injectivity and it's not known. So what I mean by surjectivity, I mean at the current time we know that if you take two hyperbolic metrics, h plus and h minus on sigma, we know that you can find a quasi-function manifold that induce h plus as metric on the upper boundary of the convex core, and induce h minus as the induced metric on the lower boundary of the convex core. But is this quasi-function manifold unique? We still don't know. Yeah, so another data on this another boundary data on this convex core is the following. So as I said that the boundary of the convex core is not smoothly embedded, but it has another structure, which we call pleated surfaces. So what is a pleated surfaces? So you can think of pleated surface as totally geodesic surface inside some three-dimensional manifold, and you start bending your surface along some geodesics, some disjoint geodesics. So as you can see here in the picture, this surface is bent along this geodesic, this closed geodesic here. Or you can think of it as like one plane, and then you take one line on this plane, and then you bend your plane along this line, as this figure on the left here. So all of these are pleated surface. So pleated surface is a surface which is pleated along disjoint set of geodesics, of simple geodesics. To formalize this, we will need to define the notion of geodesic lamination. So what do we mean by geodesic lamination? We just mean that it is a set, it is a closed set on some hyperbolic surface. It's closed set on hyperbolic surface that consists of the disjoint union of simple geodesics. So as we can see here in this example, these three geodesics form a geodesic lamination because they are three disjoint simple geodesics, so they form a geodesic lamination. And we define a measured geodesic lamination to be together the set of geodesic laminations, and we associate transverse a measure on each arc which is transverse to this geodesic lamination. So measured geodesic lamination is about like a measured geodesic lamination. It is a geodesic lamination which is closed set that consists of disjoint closed simple geodesics, and moreover it induces a measure on each arc transverse to this set of geodesics. So here it is an example we take three geodesics, the one in the red, and we put a weight on each geodesics. On each geodesic we put, for example, here W1, W2, W3, and we take any arcs transverse to this geodesics. So here, for example, we have this arc in the blue, gamma 1. It intersects this geodesic which is in the middle and has weight W2. So this arc we will associate to it a weight which is W2. If I take the arc gamma 2 in the blue that intersects the first and the middle geodesic that have weights W1 and W2, then the weight that we associate to this arc will be W1 plus W2. And for example, if we take an arc like gamma 3, which doesn't intersect any geodesic, we will just associate with weight 0 because it doesn't intersect any weighted geodesic. So this was an example about measured geodesic laminations. And the interesting for us is that any pleated surface, when we take this bending locus and the amount of bending, we will have a measured geodesic lamination. So as an example, if we take this pleated surface in that picture, which is bent along this geodesic with the angle P minus alpha, so it will give us measured lamination on sigma, which consists of this geodesic, which is bent along it, and P minus alpha, which is the angle of bending. And Thurston has made another conjecture saying that if I take two measured geodesic laminations on sigma with some conditions, then I can find a unique quasi-Fuchsian manifold that realizes two laminations as bending laminations. And we have a partial answer by Bonao and Dotal that they have characterized exactly what are the set of measured laminations that can be realized as a bending. So so at the current time, we know that if you take any two measured geodesic laminations, we know if there is a quasi-Fuchsian manifold that realize them as the bending lamination of the boundary of the convex core. We can know if it exists or not, but we still don't know if it is unique or not. The uniqueness question is still open. Next, we can talk also about another data is when the boundary is smooth. So we have seen when the boundary has a conformal structure. It's the ideal boundary that has a conformal structure. We have seen the convex core when it has structure of pleated surface. So for now, we will take some convex subset of H3. Which is invariant under the action of some quasi-Fuchsian manifold, okay, under the action of some quasi-Fuchsian representation gamma rho. So it makes sense to talk about the quotient C by gamma. And also we will get something which is diffeomorphic to sigma times 0, 1. And moreover, we know that the metric induced on the boundary of C, it is a metric with the sectional curvature bigger than -1. This comes from the convexity. And so here we have a theorem by Labourie saying that if I take any two Riemannian matrix on sigma with curvature strictly bigger than -1, then we can find the convex hyperbolic metric on sigma times 0, 1. Such that the matrix, the induced matrix on the boundary of sigma times 0 1 will be H plus and H minus. So here what we will have that here in the right, the whole manifold which is in the black is H3 by the quasi-Fuchsian representation. And this manifold here, which is in the red, it is this C, the quotient of this C by quasi-Fuchsian representation. And that's what Labourie proved. He proved that if you take any two matrix on sigma with this curvature condition, that we will find a quasi-Fuchsian manifold that realize these two datas on sigma times 0, 1. So this manifold sigma times 0, 1 is inside the quasi-Fuchsian representation. Is inside the quasi-Fuchsian manifold. So equivalently, we can say that we can find the convex hyperbolic metric on sigma times 0, 1 that induce H plus in the boundary and H minus in the boundary. And later, Schlenker have shown that this metric is unique. So now when we combine these two theorems, we get that if we take any two metric on sigma that has this curvature condition, then we will find a unique convex hyperbolic metric on sigma times 0, 1 that induce H plus in the lower boundary and H minus in the upper boundary. Yes, so this also can be seen as a smooth version of Thurston conjecture, because here this boundary is smoothly embedded inside the quasi-Fuchsian manifold. Yeah, another data which is also worth to study is the third fundamental form. So what is third fundamental form? We define it in this way. So by taking the Shop operator, which is the differential of the Gauss map by the Levi-Civita connection of the manifolds. Yes, so the framework is that we take surface sigma, which is embedded into some three-dimensional manifold. For us, this three-dimensional manifold is quasi-Fuchsian. And then we apply this formula. So we take the Shop operator, which is defined by this way, as it's mentioned there. And the third fundamental form will be the induced metric times B times B, as you can see here. So what do you need to take from that is that the third fundamental form, in some sense, measures how much sigma is curved, because the third fundamental form measures how much the normal vector, how much the Gauss map, which is the unit normal vector, is rotated. Yeah, and in this case, in the case of C, when we take a convex convex subset inside H3, invariant by some quasi-Fuchsian representation, in that case, the third fundamental form on the boundary is will be some metric that has sectional curvature strictly smaller than 1. And here we have this theorem by Schlenker saying that if I take any two metrics on sigma that has curvature, the necessary condition that the curvature is smaller than 1, and there is also another necessary condition saying that every closed contractible geodesic has length strictly bigger than 2 pi. Well, this is technical, that it will just come if you start doing things, just don't care about it. Then we can find the unique convex hyperbolic metric on sigma times 0, 1 that induce H minus, H star minus as third fundamental form on the upper boundary, and it induce H star plus as third fundamental form on the lower boundary. So this is also, it's like a smooth version of Thurston conjecture. Yeah, but this one corresponds more to Thurston conjecture about measured elimination. We will see why. We'll see why in the second part. Yeah. So yeah. So as far as so here we have seen different data on the hyperbolic on the boundary of hyperbolic manifolds, this convex hyperbolic manifolds, and we have seen how is the interaction between the metric on the quasi-Fuchsian manifold and their boundary. Sometimes we have full identification, the map is biolomorphic. Sometimes we have just existence theorem, and sometimes we have homeomorphism correspondence. Yeah, so I think I can finish. We can finish here for the first part.